Now, when evaluating trigonometric functions, unless you have the unit circle memorized, it's helpful to have the chart of the unit circle readily available when you're trying to work on your homework or on quizzes or whatever, because basically all the information we need is right here. We have the points, we have the t-value. If we are able to use the unit circle to solve it, it should all be here. And that's kind of what we're getting at and why the unit circle is important to know and useful when evaluating those trigonometric functions. So let's work on some more of the practice examples from the packet. Um, like say for example doing it pi over 2, pi over 4, whatever, just picking random points. And for each one we'll try to evaluate all 6 trig functions for them if it is possible. So let's go back to the whiteboard. And I put the unit circle right here just for a reference point. But let's start with pi over 2 and see which trigonometric functions work and which do not. So let's go ahead and do sine pi over 2. And so again, looking at that point itself, pi over 2, sine always is going to return y by definition. So at that point, y is 1, so sine of pi over 2 must be equal to 1. Cosine of pi over 2 is always x, 0. And another way you could think of the unit circle is it's a chart which has all the sine and cosine values right there. So if you look at the x coordinates all the way across, so like minus 1/2, 3 over 2, whatever, those are all the cosine values at those respective t positions. So I could kind of read this as, well, what's the cosine of 2 pi over 3? It's that. What's the cosine of that? It's that. And basically, I know all my cosines from the chart. And similarly with sines, I would just be looking for the y coordinates at each position instead. The other 4, uh, we also should be able to know them because they're just ratios to x and y. Each of the remaining 4 is just its own specific ratio. So tangent is the ratio of y over x. So in that position, it would be 1 over 0. Or notice that that one is really undefined. So I'm just going to put a red X through that. That actually doesn't really work. But then the other ones we could do cotangent. I guess I don't need to really go in any particular order. Cotangent is the reverse ratio to tangent. It is x over y. So at that location, pi over 2, it would be 0 over 1, cotangent. And the thing to remember is it's always defined, trig function of the position is always equal to the point. It's always the correspondent. Technically, the t value and the xy values are correspondent. That's what the trigonometric functions do, is they connect the dots between that correspondence between location and point. And really, cotangent of pi over 2 would just make, because of course 0 divided by anything is always 0. Now for secant and cosecant, the last of the 6 trigonometric functions. Yes, let me redo that. Another helpful thing that I like to remember about the trigonometric functions, tangent is a very fundamental trigonometric function, y over x. One way that you can remember why tangent is that is it's actually the way we find the slope of a particular point on the unit circle, the slope of the triangle that it would create. And we're going to come back to triangles later, so I'm not trying to get ahead. But um, there's a correspondence between tangent and slope. Since slope of a line, like say for example we're trying to describe a line like the lines we were looking at before, a line has a slope based on the rise over the run, like how much of this rise and how much does it run. But like if you remember formulas for that, we often refer to that as delta y over delta x. What's the change in y over the change in x? But notice that the tangent function is y over x, which is how we define slope, rise over run. And if we take that ratio, that's what the tangent does, is it finds the slope. So tangent is very fundamental because it's related to slope. And then the other, and this is how I remember the 6 trigonometric functions without having to go back to the definition every time, is I know the 3 fundamental ones. Sine is y, cosine is x, tangent is the ratio of y to x. The other ones are all just flips of those. So cotangent is the flip of tangent, secant is the flip of cosine, and cosecant is the flip of sine. So this one's a little bit easy to get mixed up, but secant is actually reciprocal to cosine. Cosine is defined to be x. If you go back to the definition, secant is 1 over x. And the way that I kind of remember the pairing about these reciprocals is that cosine starts with c, secant does not. Those are reciprocals of one another. Sine starts with s, cosecant starts with c. They're not paired together using the same starting letter. So if we're trying to remember which one is the flip of itself, cosine is x, secant is the flip of x because it doesn't start with the same letter. I don't know if that makes any sense. That's just how I remember it. But basically, cosecant would be 1 over x, 1 over 0, which of course is also undefined in this case. And then lastly, cosecant is 1 over y by definition, the reciprocal of sine, which is 1 over 1 is of course 1. So long story short, we can evaluate the trig functions for where they work. And when it comes to pi over 2, the top of the unit circle, sine and cosine are always defined. And then the reciprocals are defined in the case when we're dividing by y but not x, because we can't divide by 0. So let's go ahead and do a couple more, and then we'll wrap this one up. So let's try pi over 4, 4 pi over 3. Also, that math was rather uninteresting, just a matter of ones and zeros. But a lot of times, unless we're at those points, those quadrantal angles, not the top or the left, right, or the bottom, it's going to involve values of y and x that are not so pretty, like root 3 over 2, whatever. So let's move to, one sec while I move my whiteboard here. Um, let's try and work on pi over 4 part B of this example from the packet. So, and again, we'll just try to find the we'll try to evaluate each of the 6 trigonometric functions at those points. So we'll start with sine of pi over 4. I'll go ahead and just write them all out. Cosine pi over 4, pi over 4. And at some point, it becomes a little bit tedious because um, it's just a matter of doing fractions and various different fraction math. So you can kind of, basically I want to do enough examples to where it's making sense what I'm doing and how we evaluate them using the unit circle. But really, knowing your unit circle and remembering which trigonometric function is which is really the keys, and obviously the correspondence between t and the point. So looking at pi over 4, again, it's going to be helpful to remember where I'm at. So when I'm in my, when I'm in my brain there, I'm thinking about uh, what what is my point and what is my t value. So like at this point, pi over 4 is right here. That's this point. Notice that the unit circle that I have provided in the packet, it's a little bit easy to mix up which point is which. Like you might look at it and say, well, pi over 4, it kind of looks like it's next to that point. But if you kind of can tell, each one is it's kind of like the wheel and spoke pattern. They're kind of paired not horizontally, but they're paired along the line of the axis. Um, so I don't know if that helps you read it a little bit more clearly. But anyways, I know my t, I know my x, I know my y. So from there, that's all I need to know. So if I want to do, say, the sine of pi over 4, um, that's my location. Now I need to return sine, which is x. And if this was class time, I'd be asking you guys every single time, okay, sine, which one's that? Cosine, which one's that? So as I'm doing it, as I'm working on it, I want you to be thinking about, thinking ahead. Okay, which one is this? And because that's how we're gonna that's how we memorize it, just by practice. So drill and practice is actually very helpful here. And in the lecture quiz, I'll give you some practice to test to see if it's making sense. And in the homework, there'll be plenty more of this, I'm sure. Anyway, sine is y. So, oh, well, in this point, they're both root 2 over 2. So, okay, they're both the same. Sine of pi over 4 is root 2 over 2, as is cosine of pi over 4, because they are both value. At that 45, middle. Now, tangent, since tangent is the ratio of y to x, it will be root 2 over 2 divided by root 2 over 2. And any number divided by itself is, of course, 1. So myself a little more room here. But tangent of pi over 4 in this case is going to be 1 because we have a 1-to-1 ratio between the x and the y, or y and x coordinates. Also, noticing that this was that example we did a little bit ago, and if you've watched that video recently, you you probably remember how I mentioned that it was along the line, this horizontal line right down the middle. Like if I'm trying to split the circle directly in half between the initial point and the top point, um, it would be along the line y equal to x. That's a slope, a line with a slope 1. And the line with a slope 1 actually is correspondent to a 45-degree angle split right down the middle. So it's kind of interesting that notice that the tangent gives us 1 here. It's not a coincidence, which is actually the same as the slope of that line that we plugged into the unit circle to solve the point at that location. Anyways, let's finish the examples. The cotangent of pi over 4 is the reciprocal to the tangent. It's just the reverse ratio. So cotangent would be, I'll go ahead and put that in. It's just x over y instead of y over x. So since both x and y are the same, obviously it's going to give us the same result, 1. For the cotangent of pi over 4, secant and cosecant would be 1 over x and 1 over y, respectively. Hopefully I said that right, but in this case it doesn't matter because they're both the same. But in here it'd be 1 over root 2 over 2. And actually, since those are going to be the same, let's just erase that one to give us a little bit more space to work on this. We usually do not want to leave our answer like this. We usually want to simplify the result because this is kind of an ugly, complex fraction. It's a fraction in the denominator with radicals in there. We probably don't want to leave it like this. So to review about fraction math, when I'm taking when I'm doing these trigonometric ratios, we're going to take, most of the time it's going to be a fraction divided by a fraction, because a lot of the coordinates along the unit circle, right, most of them are not whole numbers, most of them are fractions. So when we do x over y or y over x, we're going to have fraction, fraction. So it's helpful to remember that when I'm doing fraction divided by fraction in dividing, I can always simplify that by flipping and multiplying the denominator. So the top will remain the same, and I can multiply by the reciprocal of the denominator to help simplify the fraction. Or in this case, it would be 1. When I have the reciprocal of a direct fraction for secant and cosecant, you're just flipping the fraction. Instead of being root 2 over 2, it's 2 over root 2. And as I said in the previous video, usually we want to rationalize our denominators just as a good habit. So to rationalize, I can multiply by the denominator, and that would leave me with 2 root 2 over root 4. Root 4 is, of course, 2. And the 2's will cancel because common factor. So that would leave me with root 2 over 1 or root 2. So anyways, the secant of pi over 4 simplifies quite a bit. And usually we want to simplify our answer completely as we're evaluating. And that would have been the same thing as the cosecant of pi over 4 because they were both the same. And anyways, there we have it. We have all 6 of our trigonometric functions evaluated at pi over 4. And this is the idea of how we evaluate trigonometric functions. Another thing you might wonder is, how do I evaluate it if it's not on the unit circle? Well, that's a whole nother ball game, and we might get into that a little bit, but it's harder, and we're gonna expand our ability to evaluate things beyond just this table as we progress into the chapters on analytic trig. Um, and let's stop it right here.